independencies in the exact posterior. If in the exact posterior you have these independencies, the approximation is going to be very good. If they are not, if you don't have those, if there are strong dependencies, the approximation won't be very good, and you might have. You may solve the optimization problem, get one solution, and in practice the predictions that you get by using that solution can be very bad. If you, in some cases, if you don't take into account these dependencies. This is shown in this example. In this example, you have a lot of correlations between the two variables. In this case, the exact posterior is the green curve, and you have a lot of correlations between the two variables in the posterior. And you are approximating the posterior with a isotropic Gaussian that factorizes across the two variables. And you see, you are able to match the mode, but there are regions of the exact posterior that have a large probability, and you are giving very low probability to those regions. Okay, so this is the method of variational inference. Let's have some, yeah, so when we apply this method of variational inference, we see that we should at least be able to evaluate the lower bound. The lower bound is given by this expression, and to optimize this lower bound, at least we should be able to evaluate it. The problem is that very often you might have some factors in the joint that are too complicated. Basically, the joint has to be simple enough so that when I take the logarithm, I will get a sum of the log of the factors in the joint. And the log of those factors, I should be able to integrate that with respect to Q. I should be able to integrate the log of the factors in the joint with respect to Q. If the factors are not simple, I might not be able to do these integrals. In that case, I can introduce. More approximations. I can say, instead of working with this lower bound, I'm going to introduce additional lower bounds. I can lower bound each of the factors in the joint with some simple function. And then I will introduce additional variables that will determine the form of those lower bounds, and I will optimize with respect to those additional variables. That's what is done by this local variational methods. The local variational methods, we have that they introduce some bounds over specific factors in the joint that can be useful to deal with intractable expectations. One example is the logistic function. I might have probabilistic models that include factors that depend on this logistic function. An example is given by logistic linear regression. If I have a logistic linear regression model, the likelihood is going to be similar to this. Is going to be similar to this one. In this case, I have a probit function. If I have a logistic regression model, this is going to be a logistic function, and each factor in the likelihood is going to be a logistic. It's going to have a logistic form. The problem is that the logistic function, if I take its logarithm, in general, I won't be able to integrate it. The logarithm of the logistic function is given by this expression, and if I have, for example, a Gaussian approximation, I won't be able to integrate this with respect to a Gaussian in a closed form. So to avoid this, what I can do is introduce additional lower bounds. I can lower bound the logistic function with a simple function that integrates with respect to the Gaussian. To do this, we can use a very simple method, which is that if the function is convex, for example, if I have a convex function, any tangent line to a convex function is going to give me a lower bound. So if I have a convex function like this, I can pick any point and get the tangent line at that point. And that is going to give me a lower bound on the function. And I can do this, I can find at any point in the axis, I can select a point for the function and compute the tangent line there, and I get a lower bound on the function. So I can do that with this function f, this function that I get when I take the logarithm of the logistic. It turns out that it is convex in terms of the variable z square. So I can just lower bound this function as a function of z square by taking the tangent line. Basically, f is going to be larger or equal than f evaluated at the point at which I'm going to take this tangent line, and then I'm doing a first order approximation, but with respect to the variable z square. This would be the gradient of this function with respect to z square evaluated at the point psi, the point at which I'm taking this tangent line. Basically, this has a simple form, this lower bound. You see that it is quadratic in z square, and I should be able to integrate that very easily. Yeah, the lower bound, it's always tight at the point at which I'm computing the tangent line. So at the point at which I'm taking the tangent line, the bound will be always tight at that location. This gives me a lower bound on the logistic function. Basically, I replace the value for f in this expression by its lower bound, and I get a final lower bound on the logistic function. And that bound is going to be an exponential function. So this is just I was lower bounding the logarithm of the logistic. So when I eliminate the logarithm, I get the exponential of a quadratic function. And it turns out that because it is the exponential of a quadratic function, it will be a Gaussian with respect to the variable z. This is the exponential of a quadratic function with respect to z. So this is going to be a Gaussian with respect to z, and a normalized Gaussian. And this bound can be maximized with respect to psi to find the best fit. So the point at which I'm taking the tangent line, it's going to be an additional parameter, which is an input to the directional lower bound, and I can maximize the whole lower bound with respect to the parameters of my posterior approximation and with respect to the parameters of this linear lower bound on the factors. So I'm going to have some parameters, for example, the mean and the variance of my Gaussian approximation to the posterior, and I will have some parameters psi that should be also optimized. This shows the lower bound on this logistic function. This is the function that is convex as a function of z square, and this should be like a tangent lower bounds. And each of these lower bounds results in a Gaussian lower bound on the logistic. The logistic function in this case is shown in red, and I can do a lower bound on a particular value of psi, and that results in a Gaussian lower bound on the logistic function, that it is tight at psi. At that location, the Gaussian touches the logistic function. So basically, I am lower bounding this logistic function with a Gaussian, and I will be adjusting that Gaussian so that the lower bound is as good as possible. So I will have I will be optimizing this parameter psi, which specifies the location of the Gaussian lower bound. Okay, so that's, yes.
May I ask you about the probit and logistic function?
Yes.
So I can use variation inference for probit model, but for the logistic regression, logistic function, as a logistic function, I have to use the local version of variation inference.
Yes, for the logistic function you have to use the local method, and the problem is this problem to work with to compute the expectations of the logistic function. You cannot do this, and you have to do these additional approximations. With the probit, I'm not sure if you can do variational inference. You would have to compute the expectations of the log of this probit function, and maybe there you have to do some approximations. I'm not sure if you can do that exactly also.
Because we could do it with Laplace for the probit.
Yeah, for the Laplace you can do that. You don't need to do any lower bound. For the Laplace you don't really need to do any lower bound.
If you have a logistic function, and you would like to use Laplace, you would not be able to do it.
No, with logistic you can also do Laplace. You could also do, if you have this logistic regression model, you could also use the Laplace approximation. So some considerations of this variational inference method. Basically, the approximation produced by variational inference is going to be more compact than the exact posterior distribution. We saw this in these plots. In these plots, we see that the solution given by variational inference is going to be more compact, and the reason is because we are weighting the error with respect to our approximation. And basically, our approximation takes low values. We don't care about the error, and we can afford to have large errors where our approximation is very low. And the same here. The approximation is very low in this region, and I don't care about the error in that region. Yeah, this variational inference is minimizing this Kullback-Leibler divergence, which somehow takes into account the global properties of the distribution. The Laplace was just looking at the mode, looking at the first and second derivative at the mode, and then fixing the Gaussian using just those local properties. With the variational inference method, we are looking at all the properties of the posterior distribution, because basically we are computing the error, which is given by an expectation with respect to Q of this ratio. So we will focus on, instead of just the mode, we will focus on all those regions in which Q takes large values. This variational inference approximation, a difference with respect to the Laplace approximation is that it is independent of the basis used. So this means that if we do a change of variables, the approximation is going to be the same. And the reason for this is that the Kullback-Leibler divergence, if we do a change of variables in some of the distributions and we measure if we do a change of variables in the two distributions and we measure the value of the Kullback-Leibler divergence, it's the same. The Kullback-Leibler divergence is invariant to any transformation of the variables, and this means that our posterior approximation is going to be invariant to those transformations. Computing each factor in mean field, given that the others are fixed, is a convex optimization problem that has a single solution. We saw that solution here. Basically, there is an optimal solution for this individual problem, but finding the global minimizer of the divergence, the value of all these factors, is not going to be convex in the general case. And this method is only it will only work if we can compute these expectations of the logarithm of the joint. If this is not the case, we will have to introduce some further approximations, like introducing additional lower bounds on the individual factors. So that's it regarding variational inference. We can then see how we can apply this method, the variational local method, to a logistic regression problem. That's some exercise that I plan to do in the whiteboard. So let's we can take this up. let's assume we have a data set which is similar to this data set that we described at the beginning, this for probability regression. We have some labels and some features, one vector of features for each associated with each label. We are going to assume a logistic regression model which basically specifies that the probability of each label taking value 1 or 0 is going to be given by a logistic likelihood. I use this notation but to distinguish between vectors, scalars, and matrices. The probability of each data point is going to be just, let's see. It's going to be the logistic function evaluated on a dot product between a vector, W, that represents our hyperplane, and the vector of features. And if the label is 1, I have the logistic function. And if the vector is, if the label is 0, I have 1 minus the logistic function. This model, the generative model for this probabilistic model is the same as before. It is, I assume there is a hyperplane that labels the data, but the difference with respect to the previous approach is that I assume now that the additive noise, when in the boundary of the hyperplane, follows a logistic distribution. The cumulative probability function of a logistic distribution is going to be the logistic function. So in the previous case, I had the probit function, which was the CDF of a Gaussian. Here I have the logistic function, which is the CDF of a logistic distribution. This is the probability of I, and then basically the probability of the vector y given all the features, and the hyperplane is just the product of all these factors. I have that the posterior is just the product of the joint. And the prior is a Gaussian distribution on W, a multivariate Gaussian distribution given by this expression, and the likelihood is just this formula. So the posterior distribution is just the joint, the product of this likelihood and the Gaussian prior, divided by a normalization constant, which is obtained by marginalizing out W. Then I can evaluate the lower bound. The lower bound is just given by this expression. The variational lower bound is going to be just the integral with respect to Q of W. Q is going to be my approximation. So the lower bound is just the expectation with respect to Q of the logarithm of the ratio of the joint divided by q. The problem is that here I have that I have the logarithm of these logistic functions, and I want to be able to obtain a closed form expression for this lower bound. So what I'm going to do is introduce a lower bound on this likelihood factor by making use of the lower bound on the logistic function. I have basically that the logistic function, I can introduce a lower bound. Which is just an unnormalized Gaussian. Let's call this lower bound by this with this notation. Now instead of having a logistic function, I have this lower bound that has an additional variational parameter that should be optimized to maximize the variational lower bound. So basically I have that using this bound, I can bound each of these likelihood factors. So I can, each of these likelihood factors, this likelihood factor includes two logistic functions, but I can represent it using a single logistic function by doing this transformation. I just multiply the logistic function by this term that depends, by this factor that depends on the label, and it can be shown that these two things are the same. And instead of having two logistic functions, here I have only one. So the likelihood factor only depends on a logistic function, and what I do is just replace the logistic function with its lower bound, and I get a lower bound on each of the likelihood factors. Then I can replace those likelihood factors in this variational lower bound with their corresponding lower bound. So basically I have that in the end, I have that the log of P of Y I have this lower bound on each of the likelihood of each of the factors on the likelihood. I can replace. I have here the log of the joint. I can introduce a lower bound on this log of the joint by just making use of these lower bounds, and I finally get this expression just by replacing the definition of this lower bound. So. This is the log of the joint, a lower bound on the log of the joint, and to maximize this, I can do the same approach as in mean field. I can just represent this. I would have to take the expectation of this log of the bound with respect to other factors in my variational approximation. The thing is that there are no other factors in this case. So this is just going to be my optimal update for my variational approximation. If I choose my approximation to be Gaussian. If I choose Q of the W to be Gaussian, basically if this is Gaussian with a W on W with some mean and some covariance function, basically I see that the log of the joint is just a linear function on W here, and then I have a quadratic function, so it is going to be Gaussian, and I can get the updates for these parameters just by matching these to a Gaussian distribution. Basically, I have that the variance, the inverse variance is going to be the constant, the covariance, the matrix on which I am multiplying W and W transpose and W. By just matching this to a multivariate Gaussian distribution, I get that basically S the covariance matrix is going to be, I have to consider all the quadratic terms in W. So I have a sum of a quadratic term here for each data point, and then I have here another quadratic term. So this is going to be the sum of those quadratic terms. The inverse variance is basically, in the logarithm of a Gaussian, the inverse variance is the matrix on which I am multiplying the, I have the quadratic expression for the variables. So in this is the logarithm of a Gaussian, and I have the W that multiplies this, this matrix W transpose multiplies this matrix, and I have a W. And this is the inverse covariance matrix. So I have to consider all the matrices on which I have a W times that W transpose times that matrix times W. I sum those terms. I have here I have W times that matrix W transpose times this matrix W. So I just sum all of this plus this one, and that's the inverse covariance matrix of the Gaussian. And to get the covariance matrix, I just take the inverse. And with the mean, I can do something similar, and I get the update for the mean. And this is the update for the mean. Basically, the mean in a Gaussian is it's basically the inverse covariance matrix times W. So I have to look for the terms that have basically the linear terms in W are going to give me the mean of the Gaussian. The linear terms in this case are only these ones. I have a total of n linear terms in this case, and another linear term in this case, which is M0 times this covariance. So I just sum those terms. I have the contribution of this one, which is M0 times this matrix, and I sum then the contribution of all these ones, which is each label minus 1/2 times the feature xi. And then I have to, I forgot to multiply this. These linear terms are just the inverse covariance matrix times the true mean of the Gaussian. So to get the mean, I have to multiply by the covariance matrix. And these are the updates for the means and the variances of the Gaussian. These updates, the covariance matrix and the mean, they depend on the variational parameters psi. And I should have to optimize the lower bound with respect to those parameters psi. But I'm afraid I don't have time to show that. So what I would have to do to optimize the parameters psi, I only have to replace this lower bound for the log of the joint here, evaluate, get the analytic expression for this, and then optimize with respect to the parameters psi. And I can do that just by computing the derivative and setting it to 0.
So after every iteration here, I have to copy new psi.
Yes.
By evaluating the bound.
By maximizing this this lower bound.
With respect to psi, and then again do another.
Yeah. So I can write you the optimal update for the size would be this one. This is the square root of xi transpose s. So the value of its directional parameter, psi I, is just obtained as a function of the mean and the variance of the Gaussian. I have to iterate these two updates until the whole thing converges. Basically, I update the size as a function of the Gaussian approximation, and then update the Gaussian approximation as a function of the psi parameters. And by doing this, I am maximizing a lower bound on the variational lower bound. Once I have this Gaussian, I could use it to make predictions.
Thank you, Jose. Do you have any questions? We are short of time, so if everyone has any questions, we can have it there. Okay, I see there are no questions, so thank you, Jose, for the lecture, and hopefully. And we'll see you again tomorrow. Thank you. Thank you. It was nice. Very nice. You have to work on this, right? Because I asked.
Sorry?
Have you worked on